Okay, so welcome back. Today we are going to see essentially a new concept, okay, that we've slightly been building up towards. So we're going to see determinants of matrices. I'm going to motivate what these are and their definition by starting with where we were last time, okay? So we had seen right at the end the definition of similar matrices. Okay. So what these were, and I'll just, for today, I'm only going to stick to the square case. Okay. So n by n. And what these were, well, there were, we say A is similar to B. If A is P, B, P inverse for an invertible matrix P. Okay. And the reason that we we're thinking of looking at this relation between matrices was because if we had a linear transformation between a vector space and itself, and I picked two different bases, okay, for V, then the matrix for T with respect to the first is similar to the matrix with respect to the second. Okay? So we produced, from a linear transformation, we produced two matrices, and what we think of is that A and B are both representing the matrix, or representing the linear transformation T, and P and P inverse are really representing the identity transformation from V to V, but written with respect to these two different bases. Okay, so now the question becomes how to distinguish similar matrices. Similar or dissimilar matrices. Okay, so in other words, I have two matrices, A and B, and I want to know whether they determine the same linear transformation. Okay, and this is not often obvious, right? So for example, if I give you, the matrix 2, 1, negative 3, negative 2, and the matrix 1, 0, 0, minus 1, it turns out these are similar. So this are similar. Okay. On the other hand, it's not obvious how to find the matrix P, right? So I've given you A is PB, P inverse. So what you can think is I've picked out a linear transformation. If you want, you can assume one of the matrices, like the matrix B, is the matrix with respect to the standard basis vectors. And now I've just picked out another kind of random basis and seen what this linear transformation does to that basis. And if you want to find the matrix P, you have to figure out what that other basis is, okay? Which isn't always obvious. Okay, so what we want, is invariance of a matrix which let us distinguish similarity classes. Okay, so in other words, they produce the same answer for similar matrices. Let's distinguish similarity classes. Okay, so then we can think of these kind of invariants, and you could think of these as just numbers. Okay, I'm just associating to a matrix a certain number, and I want to have that number not depend on the similarity class that I choose. Okay, so let's see examples of this. what do we have so far? The simplest invariant that doesn't depend on the similarity class is the trace. Okay, so I can immediately say if I want to know that the matrix 2, 1, 1, 1 is not similar to 2, 1, 1, 2, okay? And this is because the trace is different, right? Because trace is 3 for 2, 1, 1, 1 versus trace is equal to 4, okay? And since you have that the trace of PB P inverse is the same as the trace of B, you must have that if your matrices are similar, they have the same trace. Okay, so that's a great invariant, and the fact that it's very easy to compute, and it lets you rule out similarities, where if you wanted to rule out the existence of, some matrix P which transformed this one to the other, that might be difficult. Okay, so something that's harder, or a more kind of complicated invariant, is if A is similar to B, then they have the same ranks. Okay, so I'll just say then they have the same dimension of the kernel. So the dimension of the kernel of A is equal to the dimension of the kernel of B. Okay, so notice this is a nice fact. I mean, it gives us, more examples, so we can distinguish, for example, 2, 0, 0, 0 is not similar to 1, 0, 1, 0, 1. Okay, in this case, it's, not many things are similar to the identity, but in general, you can imagine a lot of examples where matrices have the same exact trace, but they don't have the same, one of them is, for example, invertible, and the other is not. Okay, and this is even more refined, right? It says that the kernels have to have the exact same dimension. On the other hand, it's kind of difficult to work with, right? If you want to compute the trace, you just, sum up n numbers. On the other hand, if you want to compute the dimension of the kernel, you have to put at this point, we have to put our matrix into reduced form. So that's a lot more work, okay? So let me give you the proof, because it's nice to know you can write down explicitly what the kernel of A is in relation to the kernel of B, okay? So the claim is that the kernel, let's say, of A is equal to P of the kernel of B, okay? So let's just remember that these are both subspaces, two different subspaces of Rn. So I can think of, applying the matrix P to this kernel, okay? And P is invertible, so the dimension is preserved. Okay? So how do we show this? Well, let's suppose we have x in the kernel of A. Then we know, well, since A is PB P inverse, we take P, B, P inverse of x is 0. Therefore, since P is invertible, we have that B of P inverse of x is equal to 0, which means that P inverse of x is in the kernel of B. Again, since P is invertible, this means that x is in P of the kernel of B. Okay? So that shows one direction. The other direction is suppose that x is equal to P of y, where y is in the kernel of B. Okay? Well, then we want to see that ax is 0, so we have that ax is equal to P, B, P inverse of x, which is P, B, P inverse P of y, which is P, B of y, which is P of 0, so we get 0. Okay? So any element in the kernel of A can be written as P of some element in the kernel of B and vice versa, right? If we start with P of some element of B, then we get that it's in the kernel. Okay, so this is all well and good, okay, but at this point, and this is essentially what we have, so at this point, we cannot distinguish for example, the matrices 2, 0, 0, 3 and 1, 0, 0, 4, right? So these are both invertible and they have the same trace. Okay, so how do we distinguish these? And maybe I should say these are not similar. In this case, you can, we know what P and P inverse have to look like. You can write down a matrix A, B, C, D, 2, 0, 0, 3, D, A, negative B, negative C, and solve. You can show this, but this is hard. We don't want to do this much work. Okay, so how do we distinguish them? Okay, so let's see what these matrices do, at least as transformations with respect to the standard basis. Okay, so this transformation to the standard basis takes these vectors to here, right? So it takes it to 2, 3. And now I'll emphasize what this does is it takes the unit square to the rectangle with side length 2 and height 3. Okay? So that's what the first one does. The second matrix, again, with respect to standard basis, takes this unit square to this rectangle. And the invariant that we would like to use is, well, it's going to be the fact that this area of this rectangle is different than the area of this rectangle. Okay? Now, on the other hand, this was just with respect to the standard basis. So what if I, what about another basis? Right, so I'll just take the matrix B, okay? Remember, we don't know, I have no idea what the linear transformation actually is, right? Because we haven't said what the bases are. We know that they look different, thought of as linear transformations with respect to the standard basis, but maybe, this A is with respect to the standard basis, this matrix B with respect to a random basis ends up looking identical, okay? On the other hand, I claim this can't work. So let's just, pick a random basis, and I'm going to see what the matrix B does. Well, okay. Random basis time. I don't know. It will look, this one will be V1, and that will be V2. Okay? So what does B do with respect to this basis? Well, I at least know that it sends V1 and V2 to multiples of itself. So V1 goes to itself, which I'll try to draw, and V2 just goes to 4 times itself. Okay, so here's V2, here's 4V2. Okay, so this is where it goes. Now again, we're gonna say something similar, right? In the sense that if I have V1 and V2, any random basis, I can look at the parallelogram, which I'm trying to draw. So this is spanned by 0, V1, V2, and V1 plus V2. And again, I know where this goes, right? So this goes to the parallelogram spanned by 0, v1, 4, v2, and v1 plus 4, v2. Okay? Now again, I have no idea what this volume is, so I'll just say, or this area, so I'll just call this area is x. This area I know is 4x, okay, since I'm just increasing, you don't even have to remember the parallelogram law. You just have to know that you can fit in, and my picture is, not good. You just have to know that you can fit in 4 copies, okay, of this parallelogram here, over here, so the area gets multiplied by 4, okay? A similar picture here for this transformation with respect to any basis will show that the area of the parallelogram gets multiplied by 6, okay? So, in other words, with respect to any bases, okay, the matrix A corresponds to a linear transformation. Okay, which takes, parallelograms to parallelograms of area 4 times, okay? And, that's 6 times, okay? And B multiplies areas by 4. Okay? And this means, just what we've shown is therefore A and B are not similar. If they did, they would represent the same linear transformation. But this doesn't, behave the same when it respects area. So A and B are similar, are not similar, because they can't represent the same linear transformation. Represent the same linear transformation. Okay? I mean, if they were similar, then they would secretly be the same linear transformation, just with respect to 2 very different bases. But, any linear transformation that A corresponds to is going to multiply areas by 6. Any one that B corresponds to is going to multiply areas by 4. So they can't be the same. Okay, and this is going to be our notion of determinant. Okay, so this is what the determinant measures. Okay, so let's make this precise in dimension 2. So we kind of need to check 2 things. So we need to check what the area of a parallelogram is, so we have a formula for the determinant. We also want to know that given a linear transformation, there's a number, which we'll calculate, so that any parallelogram goes to another parallelogram whose area is multiplied by that number. Okay, so what's the first thing? We want to work out the area of a parallelogram. Okay, so I'm going to keep things simple in some sense that I'm only going to deal with positive numbers. Okay, so let's just take, and what we want to do, remember we're looking at the matrix A, B, C, D. Okay, so I'm going to look at AC, that's going to be the image of one vector, BD will be the image of the second basis vector. Okay, and then the sum of the basis vectors goes to the parallelogram, or goes to the point forming this parallelogram, so it's A plus B, C plus D. Okay, and now I would like to compute this area. Well, I can do this just by computing areas of rectangles and triangles. So let me draw this picture, and then I will, oops, that's gonna interfere. Okay, so then I'll say, what the side lengths are. So let's see, so this is A, This is C. Here's A plus B, so this has to be B. This is C plus D. Similarly, now this is D. This is C. A and B. Okay. So now we can compute, well, this is BC. BC. These two triangles together are gonna, they both have D, so let's see, so this is a half DB. Okay, similarly for here. And here's a half AC, a half AC. Okay, so now you just take the area of the rectangle, which is A plus B times C plus D. So you get AC plus AD plus BC plus BD. And now we subtract all this stuff. Well, we subtract 2BC, a DB, and an AC. Okay, so this cancels, and we're left with AD minus BC, as you might expect, okay? Right, so this is all well and good. Of course, now we run into a little problem. Okay. Namely, well, I can easily plug in numbers AD minus BC. So I'll find AD minus BC is sometimes negative. Okay, which doesn't sound that good if you want it to be the area. Okay, so for an explicit example, let me just take T, which flips the basis vector, so it sends 0, 1, 1, 0 to 0, 1, and 0, 1 to 1, 0. Okay, so this corresponds to reflection over the y equals x axis. Okay, then the matrix for this is 0, 1, 1, 0. And what happens is that this square goes to the square. So, but it flips, right? So this square is preserved, but flips orientation. Okay, so if you check the AD minus BC, we'll get -1 here, and that encapsulates this flipping. Okay, so the determinant, in fact, captures the signed area scaling factor of parallelograms. Okay, so what you can think is we care about the area, so we keep track of the area plus the orientation of the basis vectors. Okay, so the simplest way to think of this is if you start with the standard basis vectors, okay, then you can fix an orientation on the plane. Let's just say fix counterclockwise, which gives us a labeling, right? So this now is, this is kind of what we've been doing implicitly in the class. We always call this the first vector, and then we think of it as the second vector, right? Well, now, if you get hit with a linear transformation, the way that you can calculate whether it's orientation preserving or conserving, or in other words, if you can determine whether the area gets flipped, again, you start at the x-axis, start moving counterclockwise and see which basis vector you hit first. If you hit the image of the first basis vector first, then the determinant will have positive area, or rather the sign of the determinant will be positive. Okay. If in this picture, if you hit the image of the second basis first, then the determinant will have negative sign, and you think of that as spanning a parallelogram with negative area. Okay? So oftentimes, this is just something that you have to kind of worry about. It's just a, difference of plus or minus, but oftentimes we can restrict to matrices which preserve orientation. And I haven't exactly said what that is. In general, but for R2 it's just a matter of making sure that, well, this picture doesn't occur, that anytime you go counterclockwise you don't hit the image of the second vector first. Okay, in that case the determinant's always positive, but you miss out on stuff, like you miss out on reflections through a line. Those all happen to reverse the orientation. Okay, so we want to show two things here. So we're going to show, well, that parallelograms go to parallelograms, okay, under linear transformations from R2 to R2. All right, and then we're going to show that there exists, so that's the first thing, and then we're going to show that there exists a number, which we're going to call determinant. So this is in the real numbers, so that for any parallelogram, the signed area, maybe I'll call it SP, the signed area of T of P is equal to the determinant times the signed area of P. Okay, so what would be bad if you're trying to find this as a definition is if some parallelograms went to, multiples of, or their area was multiplied by different factors, right? We want this number to work for all parallelograms. Okay, so first so the first part is easier, right? So a parallelogram P, and maybe I'll write this VW, okay, so VW in R2 is just the set of all vectors of the form T1V plus T2W for T1, T2 in 0, 1. Okay? So that's a parallelogram, and certainly if I take under a linear transformation, well, the set goes to T of T1V1 plus T2W, and since it's linear, this is T1 T of V1 plus T2, just T of V and W. V and W, where again, the Ti are in 0, 1. Okay, so since it's a linear transformation, parallelograms map to parallelograms. For the second part, well, this is going to follow from the following expression. So I'll write A of VW, okay, to be the signed area of the parallelogram spanned by V and W. Okay, so again, and I'm thinking of V first. Okay, so this would, if I pick V and W here, I'm getting a parallelogram of positive area. If I had WV, I would be producing something of negative area. Okay, so negative area. So this will follow, so this kind of scaling property will follow from the following facts. So A, this signed area is bilinear, okay, which means that as a function it's linear in both V and W. So in particular, if I take alpha 1 V1 plus alpha 2 V2, beta 1 V1 plus beta 2 W2, what I get is that this is equal to A of, or I can even say alpha 1, beta 1, A of V1, sorry, that should be a W, W1 plus alpha 1, beta 2, A of V1, W2, plus alpha 2, beta 1, A of V2, W1, plus alpha 2, beta 2, A of V2, W2. Okay? So that is probably the longest expression I've written in these videos. What it's saying just is if I take a parallelogram where each of the terms is decomposed into this linear combination, then I can spread everything out, distribute everything out, and just look at the areas of each piece. Okay, and then multiply by the appropriate scalars. So now if I have t going from R2 to R2, okay, and let's just say matrix with respect to standard basis is A, B, C, D, okay, then if I plug in any V and W, well, I have V, let's just say is alpha 1 E1 plus alpha 2 E2, W is beta 1 E1 plus beta 2 E2. So this goes to A alpha 1 plus B alpha 2 E1 plus C alpha 1 plus D alpha 2 E2. Similarly for beta, so I'm getting here A beta 1 plus B beta 2 plus, let me bring this up, C beta 1 plus D beta 2. Okay, so now I know that the area of VW, okay, is alpha 1 beta 2, or the signed area, minus alpha 2 beta 1. On the other hand, by admittedly tedious calculation, what you'll get is that the area of T of V, T of W is equal to AD minus BC times alpha 1 beta 1, 2 minus alpha 2 beta 1. Okay, so this is a little bit of laziness on my part, but let me just, so this seems like a terrible thing to try to multiply all the way out. On the other hand, note that A of E1 is 0. Similarly for E2 and E2, okay? So when you're multiplying all of these factors, you don't have to care about the multiples here or the multiples here. And of course, A1 E2 is 1, and E2 E1 is negative 1. Okay? So once you kind of, so you only care about the cross terms, and then you'll see that you exactly pick up this. Okay? So I admit I am being a little lazy in the calculation, though I think no one would really want me to do it. Okay? So let me just note that to see the linearity, this is not especially hard, so suffices to work in one factor, okay, and just show that it doesn't matter if you're doing the first or second factor. So if I look at a term like this, or an expression like this, you have to show that it's linear in both cases. Okay, and this is A of UW plus A of VW. Okay, so I think this case is the easiest, right? So I'm looking at multiplying. So here's my area of my parallelogram. I'm multiplying by C. Okay, so if C is positive and, well, either greater than 0 or less than 0, I'm multiplying this height by, or this length by 1. Okay, and it's visually easy, and you can also just check from the formula that this is multiplying the area by 1. If I had C being negative, then I would be looking at the area over here. Okay, And notice now that since c is negative, I'm just concentrating on this first factor, I've now switched my orientation, right? I've switched the sign, because now when I go across, I hit the second vector first. Okay, so this is why we pick up a negative area here. Okay, so let me now draw the picture for U, V, and W. I'm going to draw kind of an especially nice picture. So you should draw a couple others to convince yourself. In particular, I'm only going to have positive areas. Okay, so this is going to be U, V, and W. Okay, and the first thing to do, well, we're going to draw U plus V as well. And I think, okay, so now this square is the A of UW. Okay. Okay, so let me erase this vector V because it's not necessary for the picture. And notice that it is, oops, sorry, so if I have, this is V here. Okay, now I'm taking W, so this is U plus V plus W. And in particular, now this is A of VW. Okay, so now what I have to convince you of, let me try to switch to colors, is if I take this red parallelogram, the area is that of the blue square, okay, which is UW, plus the green parallelogram, which is VW. Okay? And the way that you can see this is if you take the green and the blue, what you're going to do, oh, I'm using up all my colors, I think. So now if I take the union of the green and the blue, and I look at this triangle, I claim that this has the same area as this triangle. So if I take the yellow triangle here, put it here, I'll get that the green and the blue minus yellow is equal to the red. Okay, or at least with the red shifted. Okay, so why is this true? Well, notice that this triangle is just precisely, this is just translating by U. So I'll say plus W, or sorry, by W. So I've taken this yellow triangle, added W, I got to this triangle, and then I fill out exactly the red parallelogram. Okay, so that's the kind of geometric proof why it's linear in the first term. Again, you have to have slightly different pictures if you have negative areas. Okay, so now we've done some work to figure out what this determinant should be. So let's look at what properties it should have. Okay, so the properties of determinant. Again, this is something that you can get just from knowing the formula AD minus BC. Okay. On the other hand, we kind of want to have geometric reasons for why this is true, especially since we're going to be going to higher dimensions, looking at determinants of larger matrices, and we want to say the same properties in 2 dimensions should extend. Okay, so let's see what should be true. Well, first, the determinant of A should be equal to 0. And now A is just going to be a matrix. Okay. This should be equivalent to the linear transformation, or any linear transformation induced by A. Okay, so with respect to any basis in R2, any linear transformation induced by A is not invertible. Okay, so in particular, if we're thinking about the standard basis vectors, the map, which just sends those to the columns of A, won't be invertible. Okay, and the reason is that you take any basis or any 2 vectors. Okay, we've seen v1, v2. We saw that A will take them to another parallelogram of area 0, which means that they takes to a line or a point. Okay, so you get like the trivial parallelograms. So therefore, A is not injective. Again, I'm kind of being a little sloppy here. Again, it's any linear transformation that could be induced by A, okay, but any choice of basis is not injective and therefore not invertible. Okay, so that's the first kind of decently useful test for a determinant, is that it can detect whether you have an invertible matrix or not. Okay, so the second property is some sort of linearity in each term, in each column. Okay, so if we think of, for example, A being A, B, C, D, then the determinant of alpha A, alpha C, B, D, or, you could put the betas, I'll put the betas here, will be equal to alpha beta times the determinant of A. Okay, so this is something we've seen before. Since the area is bilinear, you're multiplying these two vectors, multiplying u by alpha, multiplying b by beta. That will change the area by alpha times beta. Okay, so that is what's going on there. Similarly, since we showed it's linear with respect to sums in its terms, so this would be corresponding to v and w in the bilinear equation before, I can have, for example, that the determinant of a plus a prime, c plus c prime, b, d is equal to the determinant of a, b, c, d plus the determinant of a prime, b, c prime, d. Okay? So again, this is something you can get immediately from the AD minus BC formula, but it's something that's, again, you want to have that geometric intuition of adding two different vectors, looking at the various parallelograms, and you're computing this signed area. So a couple more properties. So if we have A being A, C, B, D, then if we switch two columns, right, or if we switch these columns, then this is looking at A, say, of VW versus A of WV, and by our rule for sign area, we have this, right? And similarly, we're going to have the determinant of BDAC is equal to negative determinant of A. Okay, so anytime that you're switching these columns, what you're doing is looking at the same parallelogram, but permuting the order of the vectors. Okay, and that will correspond to taking a minus or a negative for the determinant. Okay, two more. So the first one is just the determinant of 1, 0, 0, 1 is equal to 1. Okay, again, I believe that that's pretty clear. Actually, I'll just give determinant of n0, 0m is nm, something that you can get from the formula or just from computing the area of this rectangle. Okay, and finally, I think the most important, one of the more important properties of the determinant is that the determinant of AB is the determinant of A times the determinant of B. Okay? So this is something where you could, take B being A prime, B prime, C prime, D prime, multiplying it all out and computing. That's kind of terrible. So what is the proof of this? Well, AB is a composition of two transformations. And so therefore, the scaling factors multiply, right? It's as simple as that. So what I mean here is, of course, well, if I take determinant of B, let's just look with the standard basis. I don't know exactly where this parallelogram goes, but I know it goes to something of area determinant of B. Right? And that might be negative if these vectors are flipped. Okay? And now, what do I know about our scaling properties for A? Well, I know that it takes any parallelogram of any area and multiplies it by determinant of A. So again, it will go to some random parallelogram, which I don't know. Okay, so this is B, here's A, but I know its area, signed area, has to be the product. Okay, so this is something that will be true in general. I mean, all of these properties are true for n by n matrices. And essentially the reasons that all of them are true, I mean, so the determinant in higher dimensions measures some n-dimensional volume, or signed volume. The reasons that I've given for all of them, their properties holding, is the same reasons that it holds in higher dimensions. It's just a little harder to think about. An immediate corollary of this that we of course know before, right? Because we know that we're just measuring the scaling of area, but we have the determinant is a similarity invariant, like we've wanted. Okay, so determinant of A is equal to the determinant of PA P inverse. And this is just by multiplying it out. Well, for one thing, I know that the determinant of P inverse is the determinant, is 1 over the determinant of P. All right, I get this just because, well, P composed with P inverse is 1. So I'm going back to this statement. Or it's the fact that if A scales, like determinant of A, then A inverse scales 1 over that. So therefore, when you write this all out, the P inverse and the P cancel, so you get that determinant of A is equal to any similar matrix. So now let me list one more property, which is useful to actually compute the determinant. Okay, combined with the previous stuff that we've done. And I'm only going to state it for a 2x2. Well, I'll state the general theorem. It says the determinant of an upper triangular matrix, is the product of its diagonals. Okay, so an upper triangular matrix has zeros below the diagonal. So in the 2x2 case, I'm just looking at a matrix ADB 0. And the claim is that this is just AD. Okay? And what is the geometric reasoning here? Well, essentially, so if we start with b equals 0, and I say just look at the standard basis vectors, then they go to a times the basis vector times d. So the determinant is measuring the area of this rectangle. On the other hand, if I look at a parallelogram now with b not equal, so this is the b equals 0 case, this is b not equals 0, what I get is that, well, so this vector, instead of going to d, goes to a vector of the same height, but with some shifted coordinate. Okay? And now I get this parallelogram. So what I get here is a sheared parallelogram of the same height. Okay, so this height is the same and base. Okay, so the base A is the same, I've just sheared it more. And then the usual proof where I will use colors one last time. You take this triangle, plop it here, shows you that by shearing you haven't changed the area of the parallelogram at all. Okay? And that's a general fact. Anytime you see a matrix where zeros are along the diagonal, then you just know to compute the determinant. It's a general fact that you multiply the diagonal terms. And if you think about it, we kind of know, so determinants in general, kind of the way that you can compute them is by converting your matrix into reduced form. Hopefully there's a reduced form with ones in every column, okay? So that the determinant is not 0. And then you know what to do. You just multiply the diagonal terms. There's your determinant. Okay? So I guess in the next video I'm going to talk a little bit more about higher dimensional determinants, give some more properties, and yeah, thanks. Calculation.